This lecture is over 2.3, which is an introduction to combinatorics, which is a fancy way of counting. So we're going to talk about the fundamental principle of counting, so different methods of counting the different combinations of things we have, and then we're going to develop and evaluate the factorial function. So fundamental principle of counting and the factorial function. To ensure that the choices are matched up in all possible ways, you can construct a tree diagram. The tree diagram will actually be really useful when we get to chapter 3, when we talk about probability, the probability of something randomly happening. The tree diagram is going to be useful in that instance. Your PowerPoint in your book presents this information as you can always draw a tree diagram to get all possible outcomes, but when we deal with really large outcomes, we're not going to want to draw a tree diagram for 10,000 different outcomes. We're just going to be able to use the fundamental counting principle. So this example in your PowerPoint had to do with jeans and shirts or something. So the first decision, you have 2 choices. And then the second decision, you have 3 choices. So this is an example of a tree diagram of having 2 pair of pants and 3 shirts. So you end up with, you could be wearing the first pair of pants and the first shirt, you could be wearing the first pair of pants and the second shirt, the first pair of pants and the third shirt. So those are 3 different outfit choices. And then same with the second pair of pants, each one of the shirts. So here's the example here. If you buy 2 pair of jeans, 3 shirts, and 2 pairs of shoes, how many new outfits consisting of a pair of jeans, a shirt, and shoes would you have? So really you have 3 decisions to make. You have to pick what jeans to wear, what shirt to wear, and then what shoes to wear. So jeans 1, shirt 1, shoes 1, and that would encompass this branch of wearing the first jeans, the first shirt, and the first shoes. Eventually we'll talk about the probability of this randomly happen, and they'll have numbers here. So the tree diagrams are really not overly useful in this section, but they will be beneficial in chapter 3, and you'll actually have to make your own tree diagrams in WebAssign. The tree diagrams will be there, but you'll be putting numbers on top of them. Here we can focus on how many total outfits. Well, if I count them, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 total outfits. I could get that by multiplying the number of jeans I have by the number of shirts I have by the number of shoes I have to get 12 total outfits. So in this section, if they say draw a tree diagram, you don't necessarily have to do that. You can use the fundamental counting principle, which leads us to the fundamental principle of counting. So the generalization of this process is noted as the fundamental principle of counting. It says the total number of possible outcomes of a series of decisions making selected from a various categories is found by multiplying the number of choices in each decision. So multiplying the number of choices in each decision or category. So a lot of the times they're going to ask you to draw a box. I typically draw lines, so I'll say, okay, I have 3 choices, or I have 3 things I have to choose from. I have 2 pair of pants, 3 shirts, and 2 shoes. So multiplying that together, I have 12 outfits. You might also have decisions like on a dollar bill, the first 5 numbers are, the first 5 spaces are numbers, the second 5 are letters, or something like that, and so you could say, well, how many different combinations you have there. So I like to not necessarily draw boxes, but just draw lines. Enter the number of choices for each description in the appropriate box, and then multiply. So let's look at an example that's on your PowerPoint. Serial number consisting of 2 constants followed by non-zero digits followed by a vowel. So it's really important to get the idea of how this will look like. So your PowerPoint does boxes, but then they label them. The first 2 are constants, the second 3 are non-digit zeros, and the last one has to be a vowel. So letters and digits cannot be repeated in the same serial number. So I have 21 constants. So if I use 21, then I only have 20 left. So when it cannot be repeated, this decreases this number here. Non-zero digits, well, there's 9 of them. So I have 9 choices here, then I have 8 choices here, and then I have 7 choices here, because the whole part is nothing can be repeated in here. And then for the vowel, I have 5 choices. So that gives me 1,058,400. So there's 1,058,400 different ways I could write a serial number that would be in this form. If they can be repeated, then it's even going to be larger, right? So the number of constants is 21, 21, because I can use the same constant. Non-digit zeros, 9, 9, 9, because I can use the same non-digit. I can use 1, 1, 1. And then the vowel, there's still 5 choices there. So I get 1.6 million. So you can see that this is larger. When they can be repeated, generally it's larger because you could have something like B, B, 1, 1, 1A. And up here, you couldn't have that because they couldn't be repeated. So this would not be in one of the cases. So when it can be repeated, it looks something like this. When it can't, you would have something like this. So these are how many serial numbers are possible. Factorials. Factorials are useful when we get to combinations and permutations, which is on 2.4, to be able to evaluate a factorial. And the factorial function is defined in factorial as you're taking n times n minus 1 times n minus 2 all the way down to 2 times 1. So the factorial function, if we look at this example, 6 factorial, that's going to be 6 times 5 times 4 times 3 times 2 times 1. So you can usually, if you look at your calculator, usually there is a factorial button built in. Here on most computer calculators, since I assume you guys are all at a computer, you can use this factorial button here where you have 6 factorial, hit enter, and that's 720. It's the same thing as taking 6 times 5 times 4 times 3 times 2 times 1, which is 720. So you can notice the factorial button there. This next section you might want to bring a calculator for, and if you want to bring a calculator for the midterm as well, you can use that. A lot of scientific calculators, I don't have one with me at the moment, have a permutation and combination button, and they have a factorial button. So if you need any help on finding that, when you go to take the midterm, I can be there and help you do that. Also, I will let you have the computer calculator when you go to take the midterm. So you can use this computer calculator when you take the midterm. However, since you're on lockdown browser for your quizzes, I don't know if they will let you have it up. So you can learn your calculator you're using. A lot of times if you just Google the name of the calculator and the factorial button, it will show you how to find it. So our answer here, 6 factorial, was 720. So we have 720. Here I have 8 factorial over 5 factorial. So 8 factorial is 40,320. So over 5 factorial, which is 120. So if I do 8 factorial divided by 5 factorial, I get 336. In your calculator, you can plug in 8 factorial. Oops, not 65. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And get the same thing. 5 factorial, 5 times 4 times 3 times 2 times 1, 120. And we get the same thing. However, speed-wise, if you just have 8 factorial divided by 5 factorial, they'll still give you the same answer. Here I'm taking 8 factorial divided by 3 factorial divided by 5 factorial. So my answer is going to end up being 56. You have to be careful on problems like this because the way you punch it in your calculator matters. So if you take 8 factorial divided by 3 factorial and then take that times 5 factorial, you actually did not put in what you should be putting in. So if you have to be careful with order of operations with your parentheses here. That it's 8 factorial divided by all this factorial. We know 8 factorial is 40,320. 5 factorial is 120. 3 factorial would be 3 times 2 times 1, which is 6. So 6 times 120. So if I take 120 times 6, really that's 720. So here I have 40,320 over 720, I think. What was it? Yeah, 720. So now if I plug this in my calculator, 40320 divided by 720, I get 56. I get the same thing. So be careful the way you plug this in your calculator because sometimes people go up here and hit 8 factorial divided by 3 factorial times 5 factorial, and you can see that's way off. So be careful the way you plug it in your calculator. So let's look at some examples from the homework. This section is meant to be pretty straightforward. A lot of times you're just using this fundamental counting principle. A dice is rolled and a coin is tossed. Use the fundamental counting principle to determine how many outcomes are possible. So if I have a dice and a coin, I have 6 choices for my dice and 2 for my coin, right? Heads or tails or 1 through 6. So I have 12 possible outcomes. So my outcomes here are 12. Now, they ask you to construct a tree diagram to list the possible outcomes. They're wanting you to see something like heads or tails, right? If I get heads, then I really have, sorry for my computer not wanting to, I have 3, 4, 5, 6. So if I get heads, then I have the choice of getting 1, 2, 3, 4, 5, or 6. And then if I get tails, I have the same outcome of my dice. So my tree is a little weird, but. So I have 12 possible outcomes. It's either getting a head and a 1, heads and a 2, heads and a 3, heads and a 4, heads and a 5, heads and a 6. Right? Or I could get tails and a 1 and so forth. So your answer here is going to be heads 1, heads 2, heads 3, and so forth, and you'll have 12 outcomes. So hopefully this makes sense here. Cafeteria offers a special dinner that includes 1 serving of appetizer, soup, and entree for $7. So the menu has 2 appetizers, 3 soups, and 7 entrees. Oh, and a dessert, sorry. And 3 desserts. How many different meals are possible? You do the fundamental counting principle. You have a choice for appetizer, a choice for soup, a choice for a main dish, and a choice for dessert. So you have 2 appetizers, 3 different possible soups, 7 different entrees, and 3 different desserts. So your answer is going to be 2 times 3 times 7 times 3. And you need to plug that in a calculator and actually get the answer that's going to come in here. So if I do that, I have 2 times 3 times 7 times 3. So it's 126 different meal combinations. You always see like Subway or Sonic's a big one with their drinks. They write down all the different combinations of drinks you could get, and that's how they do it. How many choices do you have for different combinations? Multiply them together, and that's your total possible combinations. The serial number on a $20 bill consists of 2 letters. So I have 2 letters here, followed by 8 digits. 6, 7, 8, and then followed by a letter. So I know here is letter. Here are my possible digits. And then the last one again is a letter. Letters and digits cannot be repeated. And it doesn't say non-zero digits, so there are 10 digits. 9 non-zero digits. Okay, so they cannot be repeated. So there's 26 letters in the alphabet, right? If I use a letter, then I only have 25 left. Now digits, I start off with 10, then 9, then 8, then 7, then 6, 5, 4, 3. That's how many choices I have. I have 10 choices for this digit. Now if I use a digit, I only have 9 left. Then I have 9 choices, 8 choices, 7 choices, 6, 5, 4, 3. And then for my letter, I have 24 because I've used 2 letters up here and I can't repeat the letters. So you multiply this number together on your calculator and you get your answer. For them to be cannot be repeated. If we look at them being repeated, I would have 25, or sorry, not 25. I would have 26 times 26, right? And then 1, 2, 3, 4, 5, 6, 7, 8, and then a letter. Then I would have 10 times 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 26 again. 2, 3, 4, 5, 6, 7, 8, 1, 2, yeah. So then I would have a much larger number if I have choices of repeating digits. So the first and last letters are repeatable vowels. So A, E, I, O, and U. So there's 5 possible vowels. So I have a 5 here, and then my last one I'm also going to have 5 options. The first and last letters are repeatable vowels. The second letter is a constant. So then for constants, I have 21 choices for constants. And the digits can be repeated. And let Y be a constant. So A, E, I, O, and U are my only vowels. So I have a repeatable vowel here and here. So I have 5 choices for this block. 21 choices for this spot because it's a constant. And then I still have my 8 numbers in here, and they can be repeated. So it would be 10 times 10 times 10 times 10 times 10, 8 times, right? So you multiply all these numbers together and you get your answer for part C. Find the indicated value, just like we did on the PowerPoint before. I'm going to have 78 factorial over 75 factorial times 3 factorial. Now when my numbers are really large, I could plug this in the calculator, and if you want to do that, that's perfectly fine. But 78 factorial is 78 times 77 times 76 factorial, right? Because I can cut off it at any time because 76 factorial just goes all the way down to 1. Divided by 75 factorial. Divided by 75 factorial over 3 factorial. So 75 factorial is going to cancel, and on top I have a 78 times 77 times 76, and on bottom I have 3 factorial, which is 6. So then you can plug it in your calculator. 78 times 77 times 76 divided by 6, and I get 76,000. That's what it was. You could also just see from your calculator, if I pick 78 factorial divided by 75 factorial, and then again I have to hit divided by 3 factorial, I get my same answer. Another way you can plug it in your calculator is 78 factorial divided by, open a parenthesis, and have 75 factorial times 3 factorial, close parentheses, and hit enter. But you see here, the answer is the same, but you have to have the open parentheses You have to put your denominator in parentheses if you want to use the multiplication. Otherwise, you need to divide through everything. The top number divided by the bottom number, then that number divided by the second bottom number. So be careful on that. If you need to expand it out, be careful with it. The last one is just a formula, and it wants you to plug in 16 and 14. So I have 16 factorial over 16 minus 14 quantity factorial. So I have 16 factorial over 2 factorial. I have 16 factorial over 2 factorial. 2 factorial is 2, but if I put this in the calculator, 16 factorial divided by 2 factorial, that's going to be a really large number. But you can just write that down. So be careful with actually putting in the right number there. So 2.3 is meant to be pretty straightforward. You get the counting principles. You'll actually use some of these methods in 2.4 when we talk about permutations and combinations, which we'll do this same week. So good luck with this section. Let me know if you have any questions.